Welcome to a new episode of the ITU Journal webinar series, where you can find insights and forward-looking research on future and evolving technologies. The ITU Journal is an international journal providing complete coverage of all communications and networking paradigms, free of charge for both readers and authors. This publication considers yet-to-be-published papers addressing fundamental and applied research, building bridges between disciplines, connecting theory with application, and stimulating international dialogue. Its interdisciplinary approach reflects ITU's comprehensive field of interest and explores the convergence of ICT with other disciplines. We count on your support to make this webinar an interesting experience. Please submit your questions to the speaker using the live video wall feature. All questions from the audience will be taken during the Q&A session after the talk. The webinar is being recorded, and the recording will be made available on the ITU Journal Webinars series playlist on YouTube. We hope that you will enjoy the talk, and we encourage you to stay connected until the end for the Wisdom Corner. Live lessons. I will now give the floor to our Master of Ceremonies.
Hello, and welcome to the webinar series of the ITU Journal on Future and Evolving Technologies. My name is Alessia Magliarditi from ITU, the International Telecommunication Union, the United Nations Specialized Agency for Digital Technologies. It is my pleasure to open our fourth webinar of the fall season, kindly hosted by the i4Good, as part of the ITU Journal Discovery Series with Professor Dario Pompili. After the Q&A session, as just announced by our avatar, I will moderate the Wisdom Corner, live lessons. So please stay online. Our speaker agreed to a personal chat. He will share with us some lessons learned over the years that might perhaps be useful for some of you. I'm pleased now to introduce Professor Ian Akilditz, Editor-in-Chief of the ITU Journal and founder and president of Truva from the United States. Professor Akilditz is Ken Bayer Chair Professor in Telecommunications Emeritus at the Georgia Institute of Technology. Professor Akilditz has established many research centers worldwide, including in South Africa, Spain, Saudi Arabia, and Finland. He's Editor-in-Chief of Emeritus of Impact Factor journals and highly cited at the top of the most prestigious international rankings, visiting distinguished professors in several universities around the world. His current research interests are in 6G wireless systems, terahertz communication, metaverse, and communication in challenged environment. So I'm very pleased to give the floor to Professor Akilditz to introduce our speaker and moderate the Q&A session. Thank you.
Thank you, Alessia. Good morning, good afternoon, and good evening. A warm welcome to our global audience joining us from every corner of the world. Greetings from Santa Rita at Inatel University in Minas Gerais in Brazil. It is my distinct pleasure to welcome you to the latest installment of the ITU Journal on Future and Evolving Technologies webinar, Series Season 5, Episode 3. Today we are privileged to be joined by an excellent researcher, Professor Dario Pompili, whose pioneering work is fundamentally reshaping the frontiers of underwater communications and next-generation wireless systems. Before we begin, allow me to reflect on the transformative mission of the ITU JFET, our journal. Since its launch in December 2020, the journal has served as a beacon of open access innovation, dedicated to bridging the worlds of academia and industry and accelerating the democratization of cutting-edge research. Each submission undergoes a rigorous peer review process, ensuring that only the most impactful and forward-thinking contributions define our technological future. The journal's rapid ascent to a premier global publication is a testament to an exceptional team, including Shizu Ono-san, Bilal Jamusi, Alessia Magliarditi, you just saw her, Erika Campilongo, Maria Otero, Paulina Nash, and many others whose dedication has been nothing short of extraordinary. To our global community of researchers and innovators, we extend a continued invitation to contribute your breakthroughs and help us drive the next wave of discovery. Now it is with immense pride that I introduce our distinguished speaker, an excellent scholar, a leading researcher, a fantastic person, a cherished colleague, Professor Dario Pompili. Dario stands as one of the foremost pioneers in the field of underwater communications. Currently, he is a professor in electrical and computer engineering at Rutgers University, where he directs the Cyber Physical Systems Lab, focusing on mobile computing, wireless networking, and advanced and underwater acoustic and optical communications. He received a PhD degree in ECE from Georgia Institute of Technology in 2007, where he worked in my lab, Broadband Wireless Networking Lab. And he also previously received a laurea, combined bachelor's and master's degree, and a doctorate degrees in telecommunications and system engineering from the University of Roma, La Sapienza in Italy in 2001 and 2004 respectively. And then I asked him to join my lab. Actually, the question was, will you marry me, Dario? And he was shocked. And that was actually the question, but it was for his PhD, and he accepted, and he came to my lab, and those were fantastic 3 years we worked together, and I really enjoyed it. So in 2011, Dario received the NSF Career Award to design efficient communication solutions for underwater multimedia applications. In 2012, he received the Office of Naval Research Young Investigator Program Award, one out of the 26 awarded nationwide, to develop an uncertainty-aware autonomic mobile computing frameworks, as well as the DARPA Young Faculty Award, one out of 51 awarded nationwide, to enable real-time information processing and based on compute-intensive models for operational neuroscience. These are really fantastic successes for Dario. It's very, very competitive to receive this type of funding from these agencies. In 2015, Dario was nominated Rutgers New Brunswick Chancellor Scholar, and he published more than 200 refereed scholar publications with more than 18,000 citations. He has an 54 and I-10 index of 168 due to October 25. And he is a fellow of the IEEE and a distinguished, since 2021, a distinguished member of the ACM 2019. In the past 6 years, he has served as an editor for IEEE Transaction Mobile Computing and editor for IEEE Infocom and many other conference organization committees. Beyond these monumental professional achievements, I have had the personal privilege of knowing Dario not only as a luminary, but as an exceptional individual. As I mentioned before, we had a fantastic 3 years, and beyond that, we also kept always in touch. From the moment he joined my research lab as a PhD student, his brilliance was evident, a rare fusion of sharp intellect, relentless ambition, and unwavering dedication. Our collaboration led to seminal work in underwater wireless sensor networks, publications that continue to influence the field to this day. Dear Dario, we are truly honored by your presence. Your insights today will undoubtedly inspire and enlighten us all. Ladies and gentlemen, without further ado, please join me in giving a very warm welcome to Professor Dario Pompili.
Thank you all, and thank you, Professor Gildis, for this very detailed and warm introduction. Let's, without much further ado, let's start with the presentation. Let me see if I can share. Okay, so do you, is everything fine? Do you see my slides in full screen mode? I think
Is it full screen, Erika?
Perfect.
Erika,
right?
is it
Perfect,
Okay,
Dario.
very
Yes.
good. So thank you for the introduction. Yeah, I'm Dario Pompili from Rutgers University in New Jersey. The title of this talk is Deep Joint Source Channel Coding for underwater acoustic multimedia transmission. As Professor Akil said, I've been working on this topic for many years. I started in his lab, and but in the past years, I've always looked at traditional methods like model-based techniques to transmit underwater. Having communication underwater is very challenging. This talk is embracing in full the AI era, and so we'll see how we can take advantage of machine learning to do transmissions underwater, and so we'll have some insights on how machine learning can help us in this underwater environment. So this is the outline of the presentation. I'll have an introduction, then I'll talk about the deep joint source channel coding for images. Then I'll move on to deep joint source channel coding for videos. Videos is multimedia, but we'll have specific solutions for images and videos. The third part of this talk will change gear and will focus on analog joint source channel coding for videos. Then I'll conclude and I'll talk about future research directions. So underwater multimedia contain a lot of information and can be used for pollution monitoring, seafloor topographic mapping, monitoring underwater creatures, and data collection about interesting environmental factors. Here in this slide, you can see some examples of underwater images. Some of these are videos, and at the bottom are some papers that use multimedia. There are many applications that can be enabled and that are indeed enabled if we are able to transmit multimedia data from underwater for a variety of applications, civilian, military applications, as we can imagine, for a variety of different architectures. However, the low bandwidth of underwater acoustic channel prevents real-time communication of this rich source of information. Source coding, compression, is a way to deal with low bandwidth. However, the question of transmission through the acoustic channel is complex. Due to the nature of visual multimedia, linear analog transmission schemes can be implemented leveraging the power of machine learning in this AI era. Acoustic channel is non-stationary, and a system that uses one kind of coding and modulation scheme parameters will underperform over an extended period of time. So compression and adaptation are the ways to deal with underwater acoustic channel. However, traditional multimedia compression algorithms like H264, JPEG, JPEG 2000 are not designed with the nature of the underwater acoustic multimedia in mind, whereas a data-driven approach can make educated guesses about the received data. Furthermore, there is an opportunity to take advantage of feedback from the receiver, which can help in adaptation using a data and channel-aware coding scheme, what we call joint source channel coding, JSCC. Specifically, as I mentioned, in this talk, we'll focus on images and videos separately in the digital domain. So these first two parts are all digital. We can imagine applications like autonomous vehicles that are deployed to inspect underwater infrastructures before sending divers to inspect underwater pillars, bridges, infrastructures is very expensive and unsafe. So it's very appealing to send team of autonomous underwater vehicles that inspect the area and so as to do some triage with human on the loop, and then in case decide to send humans or other robots. For images, we imagine a point-to-point communication scenario with a feedback in which a neural network is used to variably joint source channel encode the data. Specifically, we propose a joint source channel coding architecture for images, enabling training on estimated channel state data, a neural network architecture to accommodate feedback, and a variable length encoder and decoder for adaptive joint source channel coding. The adaptivity is needed because the underwater channel changes in time and space. Something that I'm giving for granted, but it's worth saying, is that Underwater, you cannot use radio frequency communications because you will need to use very, very high power, output power. The antennas will need to be very big. It's not practical. You can only go up to tens of meters using RF. The environment is dispersive. So pretty much for medium long ranges, acoustic communication is the only technology that you can use. Of course, you can use optical, but for shorter distance, tens of meters, 100, and magnetic also, but it's very few meters, very short range. So pretty much for medium long range communications, acoustic waves, which are mechanical waves, are the only way to communicate. For digital videos, we propose end-to-end wave, which is an end-to-end learn waveform generation approach that converts input videos directly into transmittable acoustic waveforms. Specifically, we design a 3D CNN, convolutional neural network-based video autoencoder with temporal attention for compact spatiotemporal feature extraction, a vector quantization module with learnable code book that creates discrete but adaptive representations, an IFFT-based waveform generator that learns optimal complex value signals without predefined modulation schemes, a metadata-free transmission approach, eliminating from 12 to 15% overhead required by traditional methods. So more on our contributions. For videos, we propose underwater cast, an analog source channel coding architecture that envision low power, possible biodegradable, analog multimedia sensors cameras for monitoring. This is an architecture you can imagine like for, I don't know, pollution monitoring, water quality monitoring. It's a sensor network underwater. And here in this figure, you see that we have a substrate of analog, possibly biodegradable sensors. The biodegradability is a very interesting features, maybe even needed if you to deploy these sensors and in a great number without worrying to need to collect them, right? And not polluting. You're kind of detecting and you're collecting data precisely to understand the water pollution. You don't want to pollute with your own sensing tools, right? And so above this substrate, we have these buoys, and these buoys are digital devices that play the role of sink of cluster head. They collect the data that is streamed from these tiny sensors. Okay, these tiny sensors could be very simple, very low power, and very cheap, right? And they may all be only able to transmit. And then we can envision a third layer, right? In this third tier, a fusion center could be a drone that moves around and hovers on top of the buoys and collect the data. And in all this, you can do some aggregation. So specifically to support this vision, this architecture, we designed a soft cast inspired low power analog transmitter that effectively doubles the video frame rate under the same data rate conditions, and a novel receiver decoder to enhance low quality frames using motion vector predictions from preceding and succeeding video frames. The emphasis on the low power is, well, first of all, because we deploy these sensors and we want to do persistent monitoring for a prolonged time. It could be days, weeks, or even longer. And also because if we cannot recharge these batteries, then the transmission needs to be very low power, and not only the transmission, even the processing that happens at the transmitter side, with very limited ability to harvest energy from the environment. Some availability, but limited. The buoys are digital, a totally different story. They may have access to energy harvesting. And also very low power, because if you use biodegradable technology and electronics, then you need to be very low power, so tens of microwatts. That's what we're talking about for very short distances. So moving on to the first work of this talk, deep joint source channel coding for images. So we address underwater multimedia transmission in a progressive manner in this talk. We start from images and then we'll extend our approach to videos. So why starting from images? Well, images provide a simpler structure that allows us to validate the core joint source channel coding concepts. This is from in educational perspective, presentation standpoint, but also as researchers, we attack the images problem, the transmission of images problem first. Channel-aware encoding with feedback mechanism to be able to track the channel as it changes in time and space, and they provide foundation for understanding the layer representation. Once we establish the effectiveness of deep joint source channel coding for images, we will then extend these principles to the more complex domain of video transmissions. So this is the outline of our proposed deep joint source channel coding scheme for acoustic communication, as well as the variable length encoder, which is both data and channel dependent. So this overall scheme incorporates multiple components. So we have the first component is a convolutional neural network to extract features from the input images. We know that better than fully connected network, convolutional neural networks are easier to train, and they work very well with images. We are talking about supervised machine learning. So we train these algorithms offline using whatever information we have on the environment, right? And hopefully, the closer this information, the better it is from the training. But then, as we see, we have the second component is an LSTM based variable length encoder that jointly encodes based on the channel impulse response. This is something that we measure online as the transmission happens, right? And finally, we have an OFDM mapping for transmission. OFDM is very effective when it comes to transmitting multimedia data in general, even for terrestrial wireless communication, also underwater. It's a broadband transmission, so we use the whole bandwidth, but the whole bandwidth is divided into multiple sub-channels. These sub-channels are maintained to be orthogonal, and then we have, instead of doing a broadband transmissions like in a direct sequence per spectrum happens, like imagine CDMA, here in OFDM, we do parallel simultaneous narrowband transmissions on sub-channels. Of course, underwater is challenging because these sub-channels, there is a trade-off. If we have too many of these sub-channels, which is normally in general decided for OFDM to decrease the overhead, because there is a prefix, a cyclic prefix that needs to be then transmitted and then removed at the receiver. Then if we have too many of these sub-channels, Doppler is a problem in general, and specifically underwater, because the acoustic speed is 5 orders of magnitude lower than the speed of light in air. So there is a trade-off in how we use OFDM. I don't want to give too many details. If you're interested, my lab has developed better solutions than OFDM, transmitting symbols not only in frequency but also in space, as we call OSDM. So CNNs work well with images and are proved to be able to extract spatial features and correlation that helps encode efficiently with respect to fully connected network, for example. The architecture of our CNN encoder in the context of the full architecture is illustrated here in this slide. This is the detailed structure of our joint source channel coding network with feedback and description of the parameters used. COM2D layers are parameterized as output channels, kernel size, stripe, padding, and LSTM layers are hidden size, number of layers. The final transmission should be a variable depending on channel conditions. This is the key idea, okay? Because the channel, as we said, changes. We are using supervised machine learning, so we have trained things offline. So we need to have an online adaptive counterpart as we are doing the transmission. So the features from the CNN encoder can be considered a pseudo sequence of embedded features, a sentence, as we call it. And of course, there is a trade-off between the sequence length and the channel conditions, depending on the characteristics of the environment. In general, underwater, for terrestrial, in terrestrial transmissions, radio frequency traditional transmissions, we have outdoor, we have multiple paths, right? So the transmission happens not only in the line of sight, so the energy is spread across multiple paths. Indoor radio frequency, we can have tens of paths. But underwater acoustic, we may have from tens to hundreds of multiple paths. And this makes the environment very challenging because multipath creates fading, and the channel may give a lot of impairments to the transmission. Mostly in shallow water, but shallow water it's up to more or less 100 meters, right? So you often have many paths, which basically means whenever you transmit a symbol, right, which could be one beat or a cluster of beats, you have a lot of echoes, and this makes the communication very challenging at the receiver side to decode. What matters is not what you transmit and what you do at the transmitter side. What matters is what happens at the receiver side, right? If you're able to correctly decode what is being transmitted. So this figure shows the proposed sequence-to-sequence encoder and decoder. So as we input the channel feedback along with the CNN features into the sequence-to-sequence encoder, the encoder is expected to jointly, this is the key word, make the decision on the level of source and channel coding based on the feedback. So the emphasis is on jointly because in traditional model-based communications, people have used the separation principles to do source coding. You have a certain type of traffic, a certain type of data to transmit. You do the source coding, so you remove the bad redundancy that is intrinsic in the source of information, and then you do the channel coding. In channel coding now you do the opposite. You introduce good redundancy to protect your transmission from channel impairments. But this is done separately in traditional settings, because doing it jointly is very challenging, especially when you don't know the statistics about the environment, the noise. Here, using machine learning, we do jointly, source and channel coding, to extract better performance. Some people call it semantic communication, right? Semantic communication, because as we will be clear in a moment, we through the machine learning, we try to generate waveforms directly from the data that we need to transmit, in this case, images. So the idea behind that is that the variable length encoder can extract useful information from the channel impulse response on the coherence time, channel variation, and other parameters of the channel to determine the optimal level of coding. Of course, optimal is in quotation mark. Nothing is really optimal in machine learning. It's all statistical, and we try to make the best possible decisions and given information at end. So the loss function, this is a supervised machine learning, right? So we do training offline. And when we do the training, basically we have some images that we want to transmit, then we have the channel, and then we have whatever images is received at the receiver. What we are really trying to do when we do the training, which is an optimization problem that happens offline, is to try to force the images that is transmitted and the image that is received to be as close as possible. And the output is the type of waveforms given the information that we have from the channel. This is done offline. So the training of this supervised neural network is three-pronged. So we have three losses. The first one is the mean square error, where this is the formula, where this is pixel by pixel, where h and w are the height and width, I and y at are the height pixels of the input image y and reconstructed image y at, respectively. We have then the structural loss. We use the multi-scale version of structural similarity index, SSIM, which is defined in the range 0, 1. We define this loss as 1 minus m SSSIM. And the goal is to minimize the structural differences to enhance the perceptive quality at the receiver. We should remember that we are transmitting images, and these images could be seen by other humans. So it's not really just pixel by pixel, but we want to make sure that the images is perceived to be of good quality. That doesn't necessarily mean that all the pixels are correct. There is a lot of robustness in whenever we transmit multimedia. This is one of the key ideas. The third component of this loss function that we use for training is what is called the translation loss, as this formula here. F and F prime. F is the multi-scale features input into the RNN, F prime is the reconstructed features, and L is the length of the sequence being transmitted. So this loss minimizes the error between the original and the reconstructed features, while the second one looks at the images, the third one looks at the features. Features that are not inputted using some domain expertise. Features are extracted from the neural network themselves. So the final loss is a linear combination of these three components with some weights lambda. So the idea is, instead of sending everything back, the whole channel impulse response CIR, so can we save on bandwidth on the reverse channel? The reverse channel is the one going from the receiver to the transmitter. And what we want to do is transmitting images, obviously, from the transmitter to the receiver, point to point. This is the figure that extends the structure that I showed you earlier, now with the communication channel and the feedback for adaptivity. So pros for this technique is it's based on the conditions at the receiver. The feedback is customized. For example, what does it mean? If the reverse channel has high bandwidth and the forward channel has high coherence time, all the CIR can be sent, all the granular at the highest possible granular level. CIR again is the channel impulse response of the channel, so the channel is assumed to be linear and time invariant. The linearity is a good approximation, so the superposition and scaling properties apply in wireless communication in general, also underwater for acoustic mechanical waves. The time invariancy, not really, but it does inside the coherence time of the channel. So the coherence time of the channel in seconds or milliseconds is basically a window, a time window in which we can consider the channel to be not to have changed too much. Okay, that's the idea. Now within that window, we can consider the channel not only linear but also time invariant, which is of course very, very important, because now when the channel is linear and time invariant, that means that it can be defined just using the impulse response. The response, the output that you would get if you sent only one impulse. On the other hand, if the reverse channel is low bandwidth and the forward channel has low coherence time means that the channel changes fast. High coherence time means that the channel changes slowly. Okay, only compressed information should be fed back. Now, parenthesis, this coherence time is very important, right? And underwater, in any wireless communication, but underwater is even more important because it really depends on the environment. There are some situations like winter time, a lake. In winter time, the coherence time is long. It could be seconds. The channel doesn't change much. So we can learn the channel, extract as much information about the channel, estimate the channel, and use that information at the transmitter. Conversely, there are situations in which there is a sun, the sea can be choppy, summertime, thermoclines, the channel changes very fast, so the coherence time is very small. So understanding channel coherence time, TC, is critical for adaptive joint social encoding. So because this determines how coarse or fine the feedback has to be, the feedback from the receiver to the transmitter about the channel. Because at the transmitter, we are kind of trying to track this channel, okay? But not in traditional sense, but as part of the machine learning. So we can estimate TC from the channel impulse response using Doppler spread. So TC is linked to the Doppler spread. This is the Doppler spread. Basically, is the shift in frequency. This is one way to estimate the coherence time in frequency. There are other more direct ways to estimate the coherence time of the channel directly in time. Okay, I don't want to give too many details, but the idea is we need to have an estimate of how fast this channel is changing over time. That's the other thing, right? So the channel changes, of course, if you move from one location to another location, but also if you stay in the same location, the channel changes over time. A channel may become more or less benign depending on the external condition, the wind and the sun and the conditions, current, tide. So we have different mean coherence time from the watermark data set, varying from 50 milliseconds to as much as 250 milliseconds. So we use many different, this is still kind of preliminary work. We are extracting all this information from this watermark data sets that provides five different locations, and for each location, multiple recordings of the channel. And so here we see how the coherence time changes over time. And this is important to know and to track. So we will turn to the evaluation of our joint search and encoding scheme for images. So this comparison will be against these joint search and channel coding approaches in realistic experimental settings that we conducted at Rutgers. So the first one is model-based disjoint parameter selection. This is the traditional model-based communications in which we use the separation principle to disjointly optimize parameters of the transmissions, source coding, channel coding. Then we'll have another baseliner, which is the neural network-based disjoint parameter selection. So it is data-driven, this second one. It uses neural network, but it doesn't do it jointly, right? And then the third one is a reinforcement learning-based disjoint parameter selection. So reinforcement learning is an unsupervised machine learning technique that is used to do some adaptivity of the communication parameters, but again in a disjoint manner. So we assume imperfect channel knowledge the receiver across all these baseliners. These are the hardware specifications for when we talk about parameters, where we mean at the transducer side, the frequency range, the receiving sensitivity, transmit sensitivity, and then we have other parameters here. And this is the setting of our experiments. So this joint search and encoding scheme select parameters for optimal throughput. So parameters, when it comes to source coding, we talk about type and quality. So for example, JPEG 2000 are two leading standards for images, for compressing images. Quality, we can play with the quality of the images. Of course, there are trade-offs in terms of data rate needed and everything. So source coding, as I said earlier, removes the redundancy, the bad redundancy in the source, right, to be more efficient in the transmission. On the other hand, channel coding protects the communication from channel impairments. We have different families of channel coding, different types, turbo coding, LDPC, BCH, many different types, and the coding rate. So how the strength of the coding. And then, of course, we have other parameters for the transmission, the modulation symbols, the ratio between DMP, the data, and the pilot, and the number of subcarriers for OFDM, and with all the associated trade-offs. I don't have the time to detail too much. But the idea is that our approach bypasses the specific parameter selection and optimizes source channel coding jointly. Okay, so again, optimization here is in the loose sense because it's machine learning. For training, we use both underwater image benchmark data sets and the large data sets of our own collected underwater images using a Blue ROV, which is a robot, a remotely operated vehicle robot that we use to collect images underwater. So we use 80-20% train test split, Adam optimizer with a learning rate of 10 to the minus 3, and use early stopping with tolerance of 5 epochs for a maximum of 5 epochs. So in these experiments, on the x-axis, we see the kind of the SNR in dB of the transmissions, and on the y-axis we have the bit error rate and the peak SNR, which is a kind of performance metrics. So for QPSK, in A we see the bit error rate when we have different type of channel coding at different coding rates. In B we see the PSNR of the receiving images compressed by JPEG, and PSNR in C is associated with the JPEG 2000, which we call JP2, which is again two standards, traditional standards to send images, model-based traditional. So what we observe here when we compare against our deep joint source channel coding, the purple curve, is this cliff effect. And the cliff effect is some sort of threshold effect in which traditional JPEG 2000 algorithms work up to a certain point. When the channel has impairments and degrades above a certain point, then nothing works anymore, right? Whereas what we see is that in our approach, machine learning, the degradation, which we do observe as well as the SNR decreases at the receiver because of channel impairments, is smoother, is graceful, which is very important in the engineering system. Here we compare the estimated data rate achieved with these joint approaches and our joint approach. Specifically in RL, reinforcement learning, we see that, yes, it does provide a little bit better performance in terms of throughput, but as we all know, reinforcement learning is something that really cannot be used whenever the phenomenon changes too fast, because it takes long time to converge. So a deeper look into RL shows that it takes, in fact, multiple transmissions to find out the best combination of parameters for a given challenge. So the drawback is that the channel can change during the process, making it unreliable and often unusable, reinforcement learning, when the TC is under some values, when the channel changes too fast. So the lesson learned from images is that we don't necessarily provide better performance, but we are way more robust against channel impairments, which is paramount. We can have a smooth degradation of performance, as opposed to traditional model-based approaches that show this threshold effect, cliff effect. Now, let's move on to transmitting videos. Okay, so again, it's digital point-to-point, but we want to transmit videos. For us, videos is multiple frames. Okay, so it's a group of pictures. So having established deep joint source channel coding for images, we now tackle the more challenging problem of video transmission. Key differences: videos add temporal dimensions. So there is multiple frames. There might be correlation between frames. In fact, it's expected to exist, this correlation, which is there, and it's something that we need to be able to take advantage of. So there is a larger data volume in general, requires more aggressive compression because there is low bandwidth and we have more to send, that needs to be sent. Real-time constraints cannot rely solely on existing schemes. So our approach, instead of extending 2D encoders to 3D, which would have been a natural extension going from images to videos, we propose an end-to-end wave, learning the waveform itself to pack maximum information into the underwater channel. This eliminates predefined modulation constraints and metadata dependencies. So this is the architecture overview. Our architecture and end-to-end wave does end-to-end video coding and converts input videos directly into transmittable waveforms. This is the detailed architecture for underwater communication, converting input videos directly into transmittable waveforms. Again, this is a supervised technique that takes advantage of some offline training with the information that we have about the channel and the type of videos that need to be transmitted. So our solution uses a 3D CNN autoencoder to extract compact temporal spatial representation from video sequences. So given an input of a group of pictures, so we have multiple frames, each frame is considered a picture, and we look at a group of these pictures because, of course, we need to be able to extract the time dependencies across these frames. Here we have T, that is 5 frames, and this is the resolution of the images, 240 by 320. Underwater, we should not expect videos to be high quality, right? We are always talking about low quality, often black and white videos. It could be color, but much lower resolution than the resolution that we used for terrestrial video communication, multimedia communication in general, right? Because the bandwidth is very limited. We are talking about mechanical waves. The transmission loss at one point skyrockets when we increase the frequency. Okay, so the bandwidth is always limited to hundreds of kilohertz, often, or up to one megahertz, right? So the encoder performs progressive dimensionality reduction. The architecture includes 4 3D convolutional layers, channels. The temporal attention mechanism focuses on on important features, and of course it's not fully connected, so we skip connections to preserve fine-grained details, as is done in convolutional layers. So core innovation: learn waveform generation through vector quantization. So latent features processed through 20-layer MLP with residual connection. The vector quantization creates discrete learnable representation from codebook C with K512 code words. Traditional system map bits to fixed constellation points. If you're familiar with PSK, QAM, at different constellations, but the constellations is fixed. Okay, here in machine learning we do semantics, a higher level type of communication, semantic communication. So we optimize, we adapt the constellation, right, based on the channel condition. So specifically, our solution learns continuous mapping from video content to complex waveforms because of course we use sinusoidal, cosinusoidal transmissions, that adapts to underwater acoustic channel characteristics. And by doing that, we have a variable constellation points as opposed to the traditional fix when we do modulation. Layer representation are adaptive constellation points, as I said, and they change dynamically based on the video content and the channel conditions. So the key advantage is that we discover waveform patterns inherently robust, and by doing this, we are inherently robust to underwater channel impairments without manual modulation design. So we find, I mean, machine learning automatically through the training finds those invariants in the constellation that are intrinsically robust to possible channel impairments, having some information about the channel offline. So at the receiver, the channel impaired waveforms are reconstructed through complex fusion layer that combines real and imaginary components, and the MLP decoder mirrors the encoder architecture followed by 3D transport CNN. So the end-to-end gradient flow enables learning waveforms that is robust to channel distortion. So our scheme is trained offline using a multi-objective loss balancing reconstruction, quality, quantization consistency, and power constraints. We have these different components similar to what we have seen for images, but with tailoring videos. So specifically, we have these three losses. The first one is the reconstruction loss that looks at the MSE and the SSIM with this parameter alpha. The second is the commitment loss, which ensures consistency between encoded output and quantized values. It fixes the potential variable constellation size to have discrete values. And then we have a power constraint loss, which forces the output power to be below a realistic value. So the end-to-end learning, so we have a gradient-based optimization that propagates through the entire pipeline, including differentiable channel model, learning waveforms, inherently robust to distortion due to the channel. So we use different video data sets that are specific for the underwater. This is very important because we want to capture the unique marine visual characteristics. The underwater channel data sets, we use our own real at sea acoustic measurements, what is called the ACOMS data sets. I will give you the link at the end of this talk, so that if you want to use this ACOMS data sets, you can. It's publicly available. It was connected last year at the Barnegat Bay in Atlantic City here in New Jersey. So two different locations. And then we use the watermark BCH that is also available publicly. So the baseline is softcast, which is a cross-layer optimized coding scheme with traditional modulation, but that requires substantial metadata overhead to transmit chunk indices, statistics, GOP structure, so the group of picture structure, so softcast. So with respect to softcast, this is still work in progress. We can show that our solution maintains a 0% overhead, whereas softcast metadata overhead can scale and can go from 12 to 15% depending on the chuck count. So our solution shows competitive performance in low SNR regimes where typically underwater channels operate. The current limitation of our solution, and we're working on this, is that overall the PSNR is below softcast at higher SNR. Okay, so there is room for improvement, and the ongoing work is to enhance the reconstruction quality through improved loss function, deeper architecture, and extended training, so fine-tuning, and also the attention mechanism needs to be improved to force the machine learning to learn the features mostly from regions where of the frames of the videos where there is more useful content as opposed to the background of the ocean. And this concludes the second part of the talk, focusing on transmitting digitally images, the first work, and videos, the second work. So now we change gear, as I mentioned in the introduction, and we talk about how would we go about transmitting multimedia videos specifically in the context of underwater Internet of Things. And to do that, we are abandoning the idea of doing things in digital, which is very power consuming, because we need to do analog to digital conversion. Rather, we stay in the analog domain, at least in the substrate, in the sensing substrate, in the analog sensing substrate. So while this the previous end-to-end wave addresses digital video transmission, now for underwater IoT deployments, we require a different approach. So IoT has constraints, as we know. We have low power biodegradable sensors for long-time monitoring. We might need to do persistent monitoring for days or weeks or even more. We have very limited computational resources at the transmitter. We cannot run deep neural networks. And so there is a need for simple, efficient analog circuits. They are very low power, especially if the circuits if the circuitry that we're using is biodegradable and uses biodegradable components. So underwater cast is our solution. It's an analog joint source channel coding using low power circuits inspired by soft cast and a 2-to-1 Shannon encoding. So there is a compression 2-to-1. Other higher compressions, higher order compressions are also possible, but we're focusing on the 2-to-1 for reasons that will be apparent in a moment. So the key advantage is that we double the frame rate while maintaining low power consumption through all analog implementation. So transitioning to video transmission for IoT solution underwater can be done in the following ways. So the naive idea would be to assume that video is a collection of temporally adjacent frames and extend deep joint source channel coding scheme to compress them. But this, of course, would not take into account the fact that, that there is temporal correlation across frames, because, of course, when we do videos, things may not change much, right? So so the cons is that we cannot use the temporal information effectively if we just did the naive idea. And we know that underwater nodes are not computationally equipped, so they need a less complex solution. That's another reason why the naive idea is not viable. Our solution instead focuses on designing and using analog circuits that can process video frames with low power at the transmitter while leveraging softcast. So as the underlying analog video transmission scheme. So this is the architecture. The idea is to design low power analog circuits. This is an analog camera. So we don't do analog to digital conversion. We stay in the analog domain, and we built on the 2-to-1 Shannon encoding that can encode analog videos coming from low power cameras and transmit them over the underwater channel. So for transmission, we get inspiration from softcast that can use linear video transmission cast to multiple receivers. So on Shannon coding, so this is the rectangular type 2-to-1 Shannon coding. It's the simplest to look at. It's rectangular because this is the space filling curve, and this can be fully realized, and it is. We realize it in my lab, and we have papers that show how you can realize this in analog. The idea is the following: if we have 2 points, one from the x-axis, this could be, for example, one data point. It could be, I don't know, temperature. This could be humidity. You combine these 2 points, and you get this sensing source points, right? The sensing source points as the 2 coordinates here, which is the first data piece, and here, which is the second data piece. Now, without compression, you would transmit this source point, meaning you would transmit the 2 components of the source points. This point here and this point here, which are the 2 projections. Instead, how do we do compression, specifically the 2-to-1 compression? We project this sensing source point into this green dot, which is what? The analog joint source channel coded mapped point into this point. This is a projection on this zigzagging line, which I call snake, okay? Which is a space filling curve of a specific shape, rectangular. And then, instead of transmitting this point, which has 2 components, 2 data points, we transmit only 1 component, which is the length of this snake. So we transmit the length of this line in bold on this space filling curve. Obviously, the space filling curve is known and used at the transmitter and at the receiver. The receiver gets the length and can then find out the map point. So this encoding protects the Y component more in the event of perturbation of the code signal. So X and Y. On X, the noise is, of course, doing some perturbation because it's analog. So I know we all know that analog is susceptible to noise. But look at what happens on the Y. On the Y, we implicitly do some discretization without actually doing quantization. It's all analog, but we do some quotation mark quantization, which is inherently robust against some noise. So specifically, if the noise, added noise, because of the channel thermal noise at the receiver, it's less than half the distance between these two lines, which is delta. If the noise is less than delta divided by 2, then we are on the y-axis, there is no error. Okay, so we introduce some error at the transmitter to be robust. This is the 2-to-1 channel mapping. So 2 minutes I'll wrap up. We realized this 2-to-1 Shannon coding. So we have a circuit that does the compression. So basically, this is softcast. So details on softcast, it's our baseliner. So I don't need to give you too many details on softcast because this is used as a comparison. And so the idea, we have three ideas. I'll go very fast. So the first idea is that basically we have this frame FK. This is the first picture, let's say, and with the first frame FK is encoded in the y-axis. The y-axis gives some protection because of quantization. On the x-axis, we take the frame fk plus 1. We do decimations on width and length, and then we repeat. We create this repetition, this repeated 4 little frames from 1, and this is encoded in the x-axis. And then we do analog DCT, and we transmit using analog FM. The second idea, it's similar. We have frame fk, and then we look at this at the difference between frame fk plus 1 and fk, because again, temporal correlation across frames. If there is high temporal correlation across consecutive frames, then this will be mostly sparse. So we use sparsity, and then we multiply small numbers for a function to be more robust against noise. The third idea is more general, and we can look at basically a cube of points. X and Y is one frame, and T is multiple frames. We can have K frames, and by doing that, then we may decide block by block whether to transmit all the points, a subset of the points, or only 1 point. 1 point would be the representative of that subgroup. This is the key idea, and we have shown that for idea 1, that we have good results, in fact, better results in the analog domain compared to softcast, which is, however, digital, right? So to conclude, I've presented a comprehensive approach to underwater multimedia transmission across different scenarios. We have images using deep joint source channel coding with feedback and variable length encoding to capture the channel, digital videos with learned waveforms and zero metadata overhead to do some sort of semantic communication, and analog videos. I went fast on the analog videos, but the idea is to not do analog to digital conversion, stay in the analog domain, at least in the substrate, reach the buoys. The buoys are digital, then they can do whatever they want. Common thread is fully embrace AI and do joint source channel coding and go beyond the separation principle. Key innovations and these things. So further research, we are working more on the attention, and of course we can use transformers and other structures to do joint source channel coding. I mentioned CNN, but we can go beyond CNN. This is me collecting the data, and I want to conclude. And this is information about the ACOMS data set that we collected last year at here in the Barnega Bay and Atlantic City. And this concludes my talk. In this QR code, you have the link to the GitHub if you want to use the ACOMS data set. Thank you very much.
Thanks a lot, Dario. Fantastic talk. So my question, I have really many questions here. Unfortunately, we don't have time to cover all of them. So your long short-term memory model for image transmission is fascinating. And so how is the model trained to be robust to the uncertainty in the channel condition estimation? So suppose the actual channel during deployment is worse than the estimated condition the model was primed for. What is the failure mode? In other words,
Yes.
from how it works, we go to how it fails. So what is your opinion about this?
Very good. Thank you. This is the key point. Okay. So multiple dimensions to answer these questions. Okay. First of all, as you know me, you know me for many years. So we are together work on developing traditional model-based solutions, doing source coding, channel estimation, all the traditional communications before the AI era for many, many years. Modems are the modems that my lab has developed, but more and more these modems are software defined. So no one is tying ourselves and forcing us to always use one modality, one tool. You can always, depending on the channel condition, if the channel has changed a lot with respect to the channel that you use for training offline, because this is machine learning, this is supervised learning. Okay, so basically you start from a data set characterizing the channel in time and space as much as you can, and you train things offline. But as you said, and as we know, the channel changes. You're changing the location, it's just the time changes, right? So I've shown how we can adapt dynamically by having a variable length, which is in machine learning terms, the closest you can get to do some channel coding. It's not channel coding per se, it's not direct channel coding, but there is this trade-off of protecting the transmission better. Again, will it always work? No. It only works if the channel is changing, but it's changing in a way that is similar to what you have seen offline. So you get more protection. So it's possible that the channel changed so much that it's not even changing so much. It becomes something else. It becomes a channel that you didn't know. You've never seen it. If machine learning doesn't do well when supervised, when you now are faced to transmit in a channel or anyway the environment has changed phase, the transformation should be according to some physics and some rules that you have been able to capture offline. If that happens, you can always go back to your toolbox, and because these are software-defined modems, change approach and paradigm altogether. So that's exactly the experiments that we are doing, and we are trying to understand, and it's difficult because the transparency is somewhat limited in all these machine learning schemes, to what extent you can adapt within the same architecture and where you need to change gear and go back to model-based approaches. So I'm not, probably the solution is to have a hybrid software-defined hardware. Of course, I'm talking about the digital images, videos. Okay, in digital, if you have enough computational capabilities, you can change method as needed as you go, depending on what the channel is doing. Channel is changing, we know that, but is it changing in a way that you knew it offline, that was capturing the data set, or is changing in a way that is presenting you a phase that you didn't know and you don't recognize the channel? If you don't recognize the channel, you need to go back old school and do the model-based approaches.
Yeah, so I have one more question, and although I have like 5, 6 more, but we don't have the time, unfortunately.
Sure.
So your focus was more on this joint source channel coding. So my question is about where does the majority of the performance gain come from? Is it from the tailoring the source representation to the channel, or from the channel coding being inherently aware of the source's semantic importance?
Very good question. We are doing some ablation study. I've shown some preliminary results, but there is more work that needs to be done in terms of ablation study. We have made comparisons. So what we do is joints and yes, as you said, right? So machine learning supervised, and we do jointly, right? We have made comparisons against model-based techniques that don't do things jointly, so they do source coding and channel coding separately, and then we have also compared against kind of cross-layer solutions in which model-based you were trying to do cross-layer. So the make we still need, I cannot give you an exact answers like a ratio, like what is what we have seen is that machine learning, there is no reason to do it not jointly if you do machine learning, right? So we have compared against reinforcement learning that does it disjointly, and doing things jointly makes sense because there is some gain in doing things jointly. What we have seen mostly is not much in terms of performance, I'm talking about images, but the graceful degradation. So even if the channel degrades, and the channel will degrade, and we know that, you still can decode, you still see images. Whereas JPEG and JPEG 2000 at one point crashes at the receiver, and you see all black. Nothing works anymore because of this cliff effect. It's a combination of the two. We are still studying, and this requires a full ablation study that we are conducting right now to exactly understand where the gain, most of the gain comes from.
We have to be fair to the audience, because I see a question from Hongji Guo. He says, "Thank you for this very interesting talk, Dr. Pompili. These approaches are effective. I wonder if you could comment on the online use of the offline trained models. Can we train the model online considering the highly dynamic underwater channel?" Please be short, because Alessia is waiting to ask other questions.
I know. So this is a very good question. I've not mentioned that. So the training is done offline. This is supervised. And then I talk about not retraining. I never mentioned the word retraining. Retraining in full, I don't think it's possible for normal modems as of now. On the buoy, on a ship is a different story. You can retrain. But there is middle ground. We know that some layers can be retrained. We can do partial retraining. We are also investigating this aspect of partial retraining online as we get more information about the channel. I've not talked about this. It's definitely possible. A partial retraining only some layers. We know that this is a technique that is very, very effective for speech recognition, and it depends on the resources that you have on board. So not a full retrain, but a partial retrain, yes. We have, however, for now, taking a different path, which is we don't do retraining, we just adapt. But partial retraining is definitely a way to go, to be investigated, yes.
Thank you, Dario. And Alessia, it's yours. I'm sorry that we had to rush. So Alessia will ask you some questions. Dario, I'll be back. See you.
Thank you.
Thank you so much. And sorry, really, that we have to rush. I will have two questions for you, actually. The first one is, what key advice would you give to young professionals aspiring to build a career in academia or research? In your experience, what key essential skills and qualities contribute most to succeed in these fields?
Okay, so Alessia, so your question is in advice to
young researchers, to students.
Young researchers that have done the PhD, they're doing the PhD, and they want to stay in academia, go to academia. This is disconnected from the topic.
What skills, what capabilities, what qualities do you think they should have to succeed?
Yes. So okay, so it's complicated. That depends a lot on the country you're in, right? So in general, I mean,
based on your experience, I mean, with the students that you have and the student that you have been.
Of course, right? So I want to decouple the answer to my specific story. I was in Italy, then I visited Professor Kitty's lab in 2003 as a visitor, PhD student from Italy, and then I did a second PhD in the United States. So my story is different. I got passion. So follow your passions and know yourself, get to know yourself. What can I say that is not kind of cliche? It's understand what you're doing. Okay, so let me so the risk, let me put it in the context of my talk, right? Machine learning. The risk is that we get lazy, all of us, and we stop thinking, and we, because we lean too much on these very powerful techniques, and we lose knowledge, right? And we don't even risk is we think that we don't need to know, right? This is go well beyond right academia. It's a problem for all of us, right? We are leaning too much. I mean, I'm really concerned, honestly, right? All this machine learning for the young people, because it's a shortcut. It's a shortcut that needs to be used cum grano salis, okay, with intelligence. It's a technology. I don't want to be a dinosaur. I don't want to say don't use it, but it's not like a calculator. So all these examples that people do for, oh, we have been there, technology in the past, it's different because it's a technology that changes our brain. There are studies that show that the memory is affected, for at least the memory, by using ChatGPT or these machine learning tools. And so because why would you need to remember anything if you can access that information? And people could say, well, we have had Google for many years, and you search engines, it's not the same. Search engines, you still type and look and read, and now with ChatGPT you talk and you get all the information. So memory is affected. There are studies, but I suspect that it's worse than that. We can even, the brain is changed. We may even lose our logical capabilities as humans. So it is a challenge. It needs to be used properly at a certain age, not too early. And scientists are studying when, not before 13, 14 years old, when, right? And we have seen how the brain is changing, right? So the region that is focusing on processing images and videos is getting bigger and bigger and more sophisticated and more connected. And the region kind of focusing on how to interact with people is shrinking. Okay, so use this technology, but with congruence is very difficult, right? The society needs to come up with some rules.
Yeah. No, thank you so much
be
for
inquisitive
that.
and know what you're doing. You need to know. Transparency is the key. You want to understand what's happening. Okay, so it's very difficult even for experienced researchers, right? So the question from Professor Achilles was right on. Do you just go from model-based to data-driven always all the time? No. You keep your brain open, and depending on the condition, in this case it's channel conditions, but in general, you want to have multiple tools in your toolbox and use the tool that is more appropriate given the environment, given the situation, so it's an educational problem, right? So we should
thank you so much for sharing
use
that.
these techniques properly and not being used by these techniques.
Yeah, that is really a precious advice, I think, nowadays, especially. Thank you so much. My second and last question, because we're running late, unfortunately, but among your career achievements, is there one particular contribution that has a profound impact on you or on others? And what makes this accomplishment especially meaningful to you? That could inspire others, could guide others that are attending the webinar.
Okay. So are you talking about the specific achievements at the top?
That could be anything in your career. It could be anything that had an impact on you, an impact on others. Could be your, yeah. Sorry, go ahead.
So I work on several technologies. These underwater communications, I'm sure that there's impact because, as I mentioned, right? So if you know in advance what's happening underwater, you don't need to send divers, which is expensive and unsafe. I have other technologies looking at doing machine learning to do continuous monitoring of vital signs for people affected by drug-resistant epilepsy. This is also pretty important, and people with issues with circulation and heart. Academically speaking, I would say that getting my career, that was pretty big. And the career award is a very prestigious award in the United States. And often when you get the career, you get the tenure. And then from that, I kind of, that was important because I got more relaxed and I was able to go deeper and focus better on longer term. So the advice for young researchers is be persistent because there will be failures. Be persistent and don't get discouraged. Listen to others, but listen to yourself mostly, right? Listen to people that want to help you and give good critique and good comments, constructive comments. Don't get discouraged and be always integrity, as Professor Gildis has taught me. Integrity is the most very important, especially in the AI era, right? Because it's easier probably now to be less transparent. So have integrity, right? And apply your talents as you can. but integrity, persistence, perseverance, and work hard. And this are the lessons learned from in Akil's lab. So yeah, this
Thank
is
you
always
so
valid.
much. Yeah,
Maybe even more
these
now
are
in the
all
AI era.
extremely important concept and advice that you share with us. Thank you, Ian. Yeah.
Thank you, Alessia. Thank you, Daria. Fantastic.
Thank you all very much. Have a good day.
Yeah.